Good morning, everyone. Welcome to the third breakout session window of our Hawkridge Systems D2M event for 2021. Thanks for joining. This presentation is called Extreme Deformation, Advanced Simulation Techniques for Hard Problems. My name is Damon Tordini. I'm one of the product managers here at Hawkridge Systems, and I'm joined by Terrence Wu. He's our product manager for Simulia and advanced stress analysis products here at Hawkridge Systems. And he's going to be taking you through a look at how you can attack more difficult, more challenging nonlinear stress analysis problems that might go beyond some of the capabilities of the stress analysis tools you're familiar with, like those in SOLIDWORKS simulation. So Terrence will be taking us through a variety of capabilities in those tools, Simulia Abacus and other products, and hopefully it'll be informative to you all. If you have any questions, please feel free to put those into the Q&A panel on the side of the Excel events interface here, and we'll answer those as we go along. So with that, Terrence, go ahead and take it away.
All right, thank you very much, Damon. I see there's already a chat message from Dustin. That's awesome. Really encourage you guys to get in there. Let us know what you think as I'm going through the presentation, and let us know if you have any questions. Damon's going to be helping me monitor that, so we should be able to get any questions you have answered, whether that's Damon answering through text or me answering live here. Getting into it though, we are talking about extreme deformation, in keeping with the theme, the extreme theme of the conference. So for this session, want to talk about how we can deal with extreme deformation in our simulations. I'd like to start off by just defining what I mean by extreme deformation a little bit. Take a moment to do that. Then we'll do a little bit of review on some simulation theory. And once we've covered that, then we'll be able to take a look at some of the techniques for dealing with these extreme cases, how we can overcome these extreme deformations and represent those in our simulation models. Unfortunately, we only have 20 minutes here, so we'll have to move pretty quick. I won't be able to go into a ton of detail on these techniques, but I'm hoping we can do a good enough overview that you guys feel comfortable talking about them a little bit, and you can go find more information on them later and then start to use them. So what are we talking about when we say extreme deformation? When we're dealing with simulations, finite element analysis, on the one end, we often classify problems as small displacement problems. This is where we've got a model, we're applying some loading to it, we're developing stresses and strains, but the shape isn't really changing. Right? The shape that we see at the end of the analysis is basically the same as the shape we started with. In contrast, with a large displacement analysis, we're actually starting to get some shape change. The material's bending, it's flexing, it's stretching, and the strains are higher. And then when we go beyond that, that's what we mean when we say extreme, when the material's really changing shape. Like in this forging example, the material's almost flowing and the strains are very, very high. We make this distinction between small, large, and extreme because it influences the simulation techniques that we're going to have to use. For small displacement analyses, we can use linear simulation. But when we get to large displacement problems, we do need to switch to a nonlinear solution. And then for extreme cases, we need to start to use some of the special techniques that we're going to talk about in this presentation. Now, a little bit of review on nonlinear simulation. There are a few reasons that you might have to use a nonlinear simulation or you have a nonlinear problem. The first of which is the material. It could be simply that you've taken a typical engineering material and you've pushed it past its yield strength. Or maybe you're using something more exotic, an inherently nonlinear material like a hyperelastic, nitinol, something fancy like foam or fabric, or you've pushed a material so far that it's starting to crack or fail. Your problem might be nonlinear because of contact. If the contact region changes throughout the course of the analysis, you will need to use a nonlinear simulation. And of course, we also have geometric nonlinearity. So when we have our large or extreme deformations, maybe things are rotating or we're changing the direction of the load throughout the analysis, really anything that's going to change the geometric stiffness of our model. Now, this is all important because it all feeds into the math of the analysis. For a static analysis, the basic equation that we're trying to solve is always force equals stiffness times displacement. And it's really that stiffness value, that K, the stiffness matrix, that's the crucial element here. If that is constant, it's the same at the beginning and the end of the analysis, like in a small displacement analysis with a linear material, then we can use a linear simulation. But if it changes, right, if we have material that's nonlinear, we have some contact, or we have larger extreme deformations, then we do need to use a nonlinear approach. And the thing that makes a nonlinear simulation different, the reason it works when we have this changing stiffness matrix, is we deal with that change by using time increments. You'll notice that time's in quotation marks. That's because if we're talking about static analysis, there shouldn't really be any time. Instead, these time increments are then just a way for us to increment the load or other conditions that we might have applied to our model. Sometimes we'll refer to that as pseudo time. Of course, if we are talking about a dynamic analysis, then these time increments are real time increments. A little bit of review on how this time incrementation works. If we have some problem, we start at time 0, and we want to get to the end. Let's say we want to apply 100 newtons. We don't do that all in one shot like we would in a linear analysis. When we're using a nonlinear simulation, we're incrementing. We're going to apply part of the load, and then we're going to apply more of the load, and then more and more until we get to the 100 newtons. The key with this time incrementation is that at every time step, we are recalculating that stiffness matrix. Right? We're getting a new stiffness matrix based on what's happened throughout the time history. And we're able to make sure that we're getting accurate results and using appropriately sized time steps. Sometimes they're larger, sometimes they're smaller, by doing iterations at every increment. Right? Every time we increment to the next time, we need to make sure that that force equals stiffness times displacement equation is balanced. We need to have an equilibrium, and we need to have an accurate converged result. This is where we start to run into problems when we're talking about extreme deformation. Equilibrium can be really hard to achieve for these extreme cases. We might have to do lots of iterations, and we might have to use very small time steps. And this means that our analysis can take a really long time to solve or not solve at all. So how do we deal with that? The first technique that I'd like to introduce has to do with balancing the equation by using dynamic analysis. In a static analysis, we have those force, stiffness, and displacement terms. And I've just told you that it can be hard to make that equation balance. It'd be great if we could just add something to one side of the equation to balance it out. And fortunately, in a dynamic analysis, there are additional terms. We've got velocity and acceleration terms, and these inertial forces can help us balance the equation. Now, what if you're doing a static problem? The thing you're analyzing is static. Well, we can still use a dynamic analysis. And if we keep those inertial forces small, say 1% or so, then we have what we call a quasi-static solution. We're not quite keeping those forces truly zero, like in a pure static analysis, but they're small enough that the overall effect on the result shouldn't be too large, and we're able to solve the analysis by using those dynamic inertial forces to balance the equation. Okay, and so this is the first approach that you might want to think about when you're dealing with extreme deformation, is taking a dynamic quasi-static approach rather than a true static approach. Now, coming back to the time incrementation, we talked about how that's done. And the method that we shared so far, the regular time incrementation, is what we call an implicit analysis. In contrast, there is something called explicit analysis. And the big difference here is that while we have the iterations to make sure that we have an accurate result in implicit analysis, we get rid of that in explicit. Because there's no equilibrium iterations, we don't have the challenge of balancing that equation. Instead, to make sure we've got an accurate result, we just use very, very small time steps. Okay, so when we're talking about explicit analysis, there's no equilibrium iterations, so that problem's gone entirely. We use very, very small time increments instead, and those solve very, very quickly. And this makes this approach really good for high-speed dynamic analysis. But it also works really well when we have these quasi-static problems that are very unstable. It also gives us access to the next couple of techniques that we're going to talk about. We're going to shift away from talking about how we solve the problem and talk about how we set it up and deal with the mesh. I'll introduce a couple of terms here: Lagrangian and Eulerian. Lagrangian mesh is the traditional mesh we're used to. You take your nodes and elements, you map that to the material, and then when you deform it, you deform that mesh. An Eulerian mesh, though, is pretty different. Here we fix the mesh. You can see we've got a solid grid of mesh elements, and at the end we have the same solid grid of mesh elements. We've simply moved the material through those elements. If we look at more realistic example, this copper rod impact, you can see that in the Lagrangian case, those elements get really deformed. But if we look at the Eulerian case, the mesh doesn't move at all. The material simply moves through it, and so we have no mesh distortion. Now, we use the Lagrangian mesh typically in most cases because it works really well. It's easy to track the free surfaces. You can apply boundary conditions easily. It's only when we get to these extreme cases where we have a problem with the mesh being too distorted. The Eulerian mesh fixes this because you're not moving the mesh, it can't be distorted, but it's really hard to deal with. You can't track the free surfaces, you can't apply boundary conditions, and a pure Eulerian mesh by itself really isn't very practical for solving problems. So what we need to do is we need to combine these two techniques, and I'm going to talk about two different ways to do that. The first way is called ALE adaptive meshing. ALE stands for arbitrary Lagrangian Eulerian, and it combines the Lagrangian and Eulerian mesh approaches on our part to do something in the middle. Like the Lagrangian approach, the mesh is moving with the material, but only on the exterior surfaces. We'll be able to track the free surfaces and apply boundary conditions like the Lagrangian case, but we're going to allow the mesh to adjust itself inside the material, combining some of the ability of the Eulerian. You can see that we're starting with square elements, and in the end, we're ending up with rectangles. So we're not getting rid of all the mesh distortion, but it's a lot less than the purely Lagrangian case. Right? So we're somewhere in the middle. If we look at our pipe, you can see that we've got the Lagrangian, the Eulerian, and then something in the middle using that ALE technique. The elements are deformed, but they're not as extremely distorted as the purely Lagrangian case. The other technique here is CEL, or coupled Eulerian Lagrangian. CEL unlike ALE, we're not combining the two techniques on one part. Instead, we're going to have a purely Eulerian part, and we're going to have purely Lagrangian parts, and then we're just going to have those interact with each other. We're going to use the Eulerian mesh approach for the part that's undergoing the extreme deformation, but then we also have parts that maybe aren't deforming quite so much. We can use the Lagrangian mesh for those. We'll have those parts interact through contact, and therefore we won't have to apply our boundary conditions directly to the Eulerian. We'll do that to the Lagrangian parts. This technique is also useful not just for these extreme material deformations of solids, but for fluids as well. So we use CEL a lot when we're solving fluid structure interaction problems. That Eulerian mesh can be used to represent gases and liquids. To explore this a little bit more, we'll look at this rivet forming example. So we've got this rivet blank, and we're going to have the top and bottom dies, compress that around a plate. If we were doing that with a pure Lagrangian approach, this is what the mesh would look like on the rivet. And then we'd have our Lagrangian mesh on the other parts as well. If we're taking a CEL approach, though, this is what the mesh on the rivet would look like. This is a cross section. We've got our grid of Eulerian mesh, and then we're just telling the analysis which elements are filled with rivet material at the start. In 3D, it just looks like a big rectangular block. For the other parts, we're still using the exact same Lagrangian mesh. One thing to note here is that Eulerian block, it's quite a bit larger than the rivet. It's important that the mesh is large enough that anywhere that the material might deform to is captured. That way it can flow through those elements. When we run the analysis, we get results that look pretty similar in either case. It's hard to tell them apart at first glance, but when we look into the results a little bit more closely, you will notice some differences. In the pure Lagrangian analysis, the elements near the plate get pretty distorted and deformed. Of course, in the CEL analysis, we don't have that problem. The strains in the Lagrangian case look a little bit different than we might expect. Rather than getting high stresses and strains at the corners, we're actually getting them where we have the most mesh distortion. Right, so that mesh distortion is causing a problem in our analysis. It's getting caught up on the corner, and we're getting some results that maybe aren't so accurate. A good way to compare these two is by looking at the reaction forces on the two dies at the top and bottom. And you can see that for the first part of the analysis, before the deformations get too large, they actually track really closely. It's only once we start to get that mesh distortion, we have a bit of a problem, that the pure Lagrangian case gets a little bit noisy and the results get a little bit less accurate. And you can see that the CEL approach does work better here. But it does come at a cost. The CEL run took about 5 times as long as the Lagrangian run. So there is a bit of a trade-off there in order to get that additional accuracy.
Hey, Terrence, on that note, we had a question about why running a dynamic simulation can be faster, especially in these cases where something like CEL is the approach you need and it's more computationally expensive. Which technique would you use in a case like this, and why would it be better?
Yeah, so specifically for this rivet forming example, we can see that the CEL is a more accurate technique, and that would be the main reason that you would want to use it here. We're clearly able to solve it with Lagrangian as well, but we're sacrificing some accuracy, although we do get to solve faster. So the choice would be on how accurate of a solution do you need. In some cases, you won't be able to solve it with some of the lesser techniques like a Lagrangian or using implicit, and your hand will be forced to go to these more advanced techniques and use these dynamic techniques simply because that's the only way you can solve the problem. But yeah, that's a great question. I think we're pretty much out of time here, so I'll do a quick recap. We've talked about some different ways that you can approach these extreme deformation problems. We know that we're definitely going to need to use nonlinear simulation. We should probably start to look at using a dynamic or at least a quasi-static approach. We may need to consider switching from implicit to explicit time incrementation. And if things get really intense, then we can start to use that Eulerian mesh either with ALE or CEL. So that's about it for this presentation. I hope you guys found it useful, and thanks very much for attending. I'd love to know if you did learn something new. So maybe before you hop out of the session, if you could just leave a message in the chat and let me know if you did learn something new today, that'd be great. Dave and I will keep the session open for a few minutes longer in case there are any additional questions. Or if you come up with any questions after the conference, please feel free to get in touch with us afterwards. Once again, thanks very much for attending. All right, got some questions here. Start at the top. I think that's earliest. Ross is asking, are these solving techniques available in SOLIDWORKS or only Simulia? Some of the more basic techniques, just the simple implicit nonlinear analysis, that is available in SOLIDWORKS. Some of the more advanced techniques, explicit solving, ALE, CEL, those are only available with the Simulia tools. So Michael has a question here on examples of papers showing the techniques applied to materials going through phase changes. We won't be able to model phase changes with any of the techniques we've talked about today, but you did also ask about fluid phase, and yes, CEL can be used to represent fluid structure interactions, so there is that.
Yeah, I think, Terrence, we may have seen some applications where you could try to mimic some kind of fluid that maybe has its viscosity go way up at certain temperatures. But as far as true phase change, like solidifying into a solid material and then behaving in that way, we probably don't have that capability. But there are other ways we can try to mimic or predict phase change in some of the other tools we have, mainly the fluid flow simulation tools. For example, SOLIDWORKS Plastics is for simulating the injection molding process, which forms a molten plastic into a solid part. And then SOLIDWORKS Flow simulation has some tools to predict where you might have things like cavitation or where a gas could potentially condense into a liquid. Those are a little bit different than the CEL approach.
And there's a question here about why adding additional variables, I presume referring to the dynamic approaches for static problems helps. And in the question statement here that maybe iterations are no longer required. If you're still using an implicit solution, you do still need that equation to balance even with the additional terms. But the additional terms help because they give us additional terms to use to balance the equation. So dynamic approaches naturally tend to balance a little more easily than the purely static approach.